In the last video, we got to see a variety of different insertion methods, and in this video, I'm going to show you a few different ways of deleting data from our linked list. We're going to take a look at a deletion from the front, a deletion from the rear, and a general deletion, starting with our delete front. The idea of our delete front method is basically, we're going to check to see if the size is greater than 0, or it doesn't equal 0. And if it doesn't equal 0, then we simply just update the front to point to the thing that is after it. If the size does happen to be 0, then what we're going to do is we're going to raise an exception, right? So we could say an exception, I would just say like index out of range is probably an okay one to use there. And then we'll just decrement the size afterwards since we deleted something from our linked list. So this is a general process of a deletion from the front, right? It's very easy. We just move the front forward 1, we reduce the size by 1, and we are done. This is a nice clean constant time operation. Now the deletion from the rear is where we start to run into a bit of trouble. And this is actually one of the main places where a doubly linked list is going to be important for us. With the deletion from the rear, we could start the same way. But what we'll quickly realize is that there's no way to get rid of the rear value. There's a reason for this. So if you take a look at a linked list, right? Suppose you have something like this. In order to remove the rear, we have to make this value the new rear, because when we delete this, this one becomes the new end. However, in order to make this the new rear, we need some sort of reference to it. In the doubly linked list that we'll take a look at in a future video, what we could do is we could start at 3, and then we would have a pointer that points backwards to 2 to show us what the previous value is. In this singly linked approach, we only have it in one direction, so I can only see what comes next, not what comes previous. So in order to find that previous value, we actually have to do iteration. What we have to do is something similar to our general insertion, where a holder is going to equal self.front. We're going to set a previous equal to none. And then all I'm going to do is I'm going to iterate while holder.next does not equal none. When you get to holder.next equals none, if the next value is none, that is the rear of the list, right? And we just do on each iteration previous equals holder, holder equals holder.next. We've seen that sort of idea already, right? And then what we could do here is we could say self.rear equals previous. So basically it will be the thing that is previous to the current rear. And then what I do is I just say self.rear.next equals none. So basically what I do is I make the rear the thing that came previous to the one that we're removing, and then I set its next to be none to say that nothing follows it, effectively removing the current rear from the actual sequence itself. After this, we take self.size, we reduce it by 1, right? And that's really all we need to do here. Just on this if statement here, I'll create an else where we raise an exception to say index out of range. And there we go. So you can see that this method is not as efficient as we would like. This gives us about ON. It's still not too bad. We do have to iterate the whole list to get rid of the value, but it's only really one of the methods that's doing this, so it's not terrible. However, we can improve this with our doubly linked list. So that's going to be one of the main motivations I want you to keep in mind when we explore that in a future video. For now, though, let's just move on to finish up our deletion by taking a look at a general delete that just takes in a value, or that just takes in an index, rather. We don't need a value, of course, because we're not inserting, right? So with this general delete, we follow a similar kind of principle to the general insert, right? We say if the index is greater than self.size, right, then we're not going to do the deletion because it would be out of range, right? So that would be the case there. And then we do a similar else if the index is equal to 0, then we're just going to delete from the front. If the index is equal to the size, of course, we will just delete from the rear, right? And then in the general else, what we do is we say holder equals self.front, previous equals none, I equals 0, and then we just go through, we say, well, I does not equal to index, previous equals holder, right? Just iterating through and keeping track of the holder and its previous value. We increment I by 1. All of this is same sort of idea. And then basically, in order to remove a value from a linked list, right? So if we have a reference to the current value and its holder, or its previous, right? So suppose we wanted to remove this value. all you would do is we would take this previous pointer to next, and we would have it point all the way to 3. So we just remove the pointer to the thing that's in the middle, right? That's what we're doing for our deletion. And the way that we do that is we just say previous.next equals holder.next. Since holder has the value at the index that we're trying to remove, we put previous.next to point to holder's next value, right? And then all we do is just decrement the size by 1, since we've now removed a value from our linked list. This, similar to our general insertion, is going to have a worst case on, right? The delete front is our best case, which is constant time. Delete rear is also on, right? So that's the general time complexity of this deletion. Let's give these a test out and see what happens, right? So we saw that this was our list when we did all of our insertions, right? So now if I do a delete from the front, what you'll see is that the value 1 should be gone. That's what we see as a result. If I do a delete rear, the value 2 should be gone. And that's what we see as a result. And now if I just do a delete at a general index like 1, we should see 4 is gone, right? So you can see that this does basically follow the general ideas of what we would expect. You could try this out with really any index, and you should see that it deletes out that index from our linked list, and everything is good to go. So with this, we now have insertions and deletions. What I want to do in the next video is I want to demonstrate to you the idea of a doubly linked list. This one is going to give us a much better time complexity for specifically our deletion from the rear, because it will allow us to have a previous pointer. It also helps to simplify some of our iterations so we don't have to keep track of a previous node. So it's a bit of a better improvement on this with the cost of being a little bit more memory to actually store the data structure. So we'll take a look at this idea in the next video. So thanks so much for watching. I'll see you in the next one.